What's up, Chem peeps? Who is ready for another free response practice? A rigid 8.20 liter flask contains a mixture of 2.50 moles of hydrogen, 0.500 moles of oxygen, and sufficient argon so that the partial pressure of argon in the flask is 2.00 atmospheres. The temperature is 127 degrees Celsius. Part A. Calculate the total pressure in the flask. Let's recall Dalton's law of partial pressures. Boom. The sum of the individual partial pressures of the gases equals the total pressure of all of the gases. So we are already provided with the partial pressure of the argon gas, 2.00 atmospheres. If we could somehow determine the partial pressure of the hydrogen and the partial pressure of the oxygen, we could then determine the total pressure in the flask. We're given the volume of the flask, the number of moles of each of those gases, and the temperature. You know what this sounds like, don't you? Pivnert. Alright, in green, I'm going to do a Pivnert calculation for hydrogen. Partial pressure of the hydrogen in an 8.20 liter flask equal to 2.50 moles times our gas constant for atmospheres times our Kelvin temperature. 127 plus 273. Quick trip to the calculator. Times 0.0821. Enter. Times 2.50. Enter. Divided by 8.20. Enter. Partial pressure of the hydrogen, 10.0 atmospheres. Boom. Now, if only we could figure out the partial pressure of the oxygen. You guessed it, another Pivnert calculation. This time we're looking for the partial pressure of the oxygen. It's still in an 8.20 liter flask. We've got 0.500 moles, my gas constant still the same, and we're still at 400 Kelvin. Quick jump to the calculator. 0.50 times 0.0821, enter, times 400, enter, divided by 8.20, enter. 3 sig figs, the partial pressure of our oxygen is 2.00 atmospheres. 2.00 atmospheres. So, now that we know the partial pressure of the hydrogen, partial pressure of the oxygen, and partial pressure of the argon, all we have to do is add those together. I'm not even gonna use a calculator. 14.0 atmospheres. Boom. Part B. Calculate the mole fraction of hydrogen in the flask. Well, remember that mole fraction is our moles of hydrogen over the total moles of gas. Now, scoot back up and take a look at the problem. We are already told the number of moles of hydrogen, 2.50. Boom. Our total moles of gas are going to be the 2.50 moles of hydrogen plus, scoot back up here. Oh, we're already told the number of moles of oxygen. Boom. Plus, our last gas is argon. Scoot back up here. Aw, man. College board, always making me work for it. I'm not given the moles of argon, but I am given the partial pressure of the argon, the volume that argon occupies, the temperature of that argon. So you guessed it, another Pivnert calculation. Partial pressure of the argon times the volume of our container, for number of moles, times our gas constant, times our temperature in Kelvin. Calculator. 0.00 times 8.20, enter. Divided by 0.0821, enter. Divided by 400, enter. Our number of moles to 3 sig figs, 0.499. So I'm going to add that to my mole fraction, and I'm going to finish my mole fraction calculation by taking my moles of hydrogen and dividing it by the total number of moles of gas. 2.50 divided by parentheses 2.50 plus 0.50 plus 0.499 close parentheses. My mole fraction is 0.714. Boom. Again, no units with the mole fraction. This is just telling us how much of the gas sample is hydrogen gas. The mole fraction 0.714, it's mostly hydrogen gas. And think about it, we've got 2.5 moles of hydrogen compared to 0.5 moles of oxygen and roughly 0.5 moles of argon. So it's mostly hydrogen. Makes sense. Math, fractions, the good old days of elementary school. Just cranking it up a notch. Which brings us to part C. Calculate the density in grams per liter of the mixture in the flask. Alright, density is equal to total mass in grams per volume in liters. Now we know, because we studied this problem intensely, that the volume of our gas sample, of our mixture of gases, is 8.20 liters. Boom. That's the easy part. But now I need to get the total mass of my gases in that 8.20 liters. Well, in the previous part, we just determined the number of moles of each of the gases in our sample. Easy enough to convert those to grams. You could have done this in pre-AP Chem to get the total mass of the gases in that flask. So I'm going to take all my number of moles of gases, set up some conversion factors. Boom. Head to your trusty periodic table if you're unsure about where I got these molar masses. Then, just hang out with your good friend calculator. 2.50 times 2.016 is 5.04 grams of hydrogen gas in our container. 0.500 times 32.0 is 16.0 grams of oxygen gas in our container. 0.499 times 40.0 is 20.0 grams argon in our container. To get the total mass of the gases, we're going to add these masses together. Plus 16 plus 5.04 is 41.0 grams total. 41.0 grams. Divide that by my volume. Divide by 8.20. The density of our mixture of gases in grams per liter, 5.00 grams per liter. Boom. Careful with your sig figs. You've got addition, multiplication, division. Those sig figs are never going away. The mixture in the flask is ignited by a spark, and the reaction represented below occurs until one of the reactants is entirely consumed. Part D. Give the mole fraction of all species present in the flask at the end of the reaction. All right. First thing I'm going to do is figure out which one of these reactants is entirely consumed. I know I've got hydrogen and oxygen in my flask. I'm going to set up not an ice table, but an ICE table. This is a great way to figure out limiting reactant and which reactant is in excess. Because it's not an equilibrium ice table, it doesn't have to be in concentrations or pressures, we can just use number of moles. Remember that initially we had 2.50 moles of hydrogen and 0.500 moles of oxygen. No water initially before that spark is brought to the flask. Remember, the change is going to occur stoichiometrically, and the relationship between hydrogen and oxygen is a 2-to-1 relationship. So if I used up all 0.500 moles of my oxygen, I'm going to use up 1.00 moles of hydrogen, or twice that amount. And I'm going to make 1.00 moles of water vapor. So at the end, I'm going to have 1.50 moles of hydrogen remaining, no oxygen remaining, and the formation of 1 mole of water vapor. Now I want the mole fraction of all species. So let's first do the mole fraction of hydrogen. Remember, it's the moles of hydrogen over total moles. So it's going to be 1.50 moles of hydrogen over 1.50 moles of hydrogen plus 1.00 moles of water vapor, plus, don't forget that inert argon. We still have 0.499 moles of argon in our flask. Calculator. 1.50 divided by parentheses 1.50 plus 1.00 plus 0.499. Close parentheses. Our mole fraction of hydrogen, 0.500. So think about this. We have 3 moles total of gas in our flask. 1.5 moles of that is hydrogen. In other words, half of it is hydrogen. So our mole fraction, 0.5. Oh my goodness, math coming through in the clutch. We don't have any oxygen remaining, so I'm not going to complete a mole fraction calculation because we only want the mole fraction of all species present and there isn't any oxygen. But let's do water. We've got 1 mole of water vapor over total moles. Boom. Jump to your calculator. 1.00. Divide by parentheses 1.50 plus 1.00 plus 0.499. Close parentheses. Our mole fraction for water vapor, 0.333. Makes sense because there's a fewer number of moles of water vapor than there is hydrogen. So the mole fraction of water vapor is going to be less than the mole fraction of hydrogen. All right, and then finally, don't forget we've got that argon that's in there inert, unreacted. We've got 0.499 moles of argon over our total moles. Boom. Let's do this. 0.499 divided by parentheses 1.50 plus 1.00 plus 0.499 close parentheses. Our mole fraction of argon, 0.166. Now think about it. You could have come up with the mole fraction of the argon by subtracting 0.5 and 0.333 from 1. Fractions in decimals are just so much fun. That's it for this vid. Have a fantastic day.